Reference frames, displacement, and velocity. Speed, distance, and time didn't require us to define where we started and where we ended up. They just measure how far we traveled and how long it took to travel that far. However, much of physics is about knowing where something is and how its position changes with time. To define position, we have to use a reference frame. A reference frame lets us define where an object is located relative to other objects. For instance, we can use a map to compare the location of different cities, or a globe to compare the location of different continents. Reference frames are especially useful to us when describing how objects are moving. You're currently sitting at your desk. Are you moving right now? If your reference frame is your classroom and you're seated at your desk, then no, you are not moving. However, if your reference frame is the sun, then yes, you are currently traveling through space in an orbit. If you're running after a bus and you and the bus are both traveling at the same speed, then your relative speed would be 0. The distance between you and the bus would not be changing. However, if a bystander who was standing still on Earth's surface was watching this happen, they would see both the runner and the bus as having speed s. The bystander would be in Earth's reference frame. In this class, we will almost always be in the reference frame of being stationary on Earth's surface, witnessing other things moving around. In this course, we will be solving problems in 1 and 2 dimensions. We will start out with one-dimensional motion. Typically, we use the x-axis for that direction. Plus x will usually be to the right, negative x would then be to the left. We could define it the opposite way, with negative to the right and positive to the left, but unless specified otherwise, this is what we'll assume. We can also think about compass directions in terms of positive and negative. For example, north would be positive and south negative. The symbol for position is x. Now that we understand how to define position, we can talk about a change in position, called displacement. The symbol for change is the Greek letter delta, or this triangle symbol. So, delta x means the change in x, or the change in position. X with a little 0 subscript is called x naught. It means the initial position, or the position at a time of 0. We will use 0 subscripts throughout this course to represent initial conditions. In English, the word naught means nothing or 0. Displacement describes how far you are from where you started, regardless of how you got there. For instance, if you drive 60 miles from Pennsylvania to New Jersey, so we have our initial position here, x naught, and we're going to drive 60 miles east. And then you drive 20 miles back towards Pennsylvania. So x with no subscript represents the final position, although sometimes you will see it written as x sub final or x sub f. Alright, so we traveled 60 miles east and then 20 miles west. Therefore, we've traveled a total distance of 80 miles. That's what our car odometer would read. However, our displacement is just 40 miles from where we started to where we ended up, this purple vector right here. We can calculate displacement with the following formula. Change in x is your final position minus your initial position. So here, our final position was at 40. Our initial position was at the origin, 0, which is why our displacement was 40 meters. Measurements of distance can only be positive values, since it's impossible to travel a negative distance. Your car odometer reads distance. It just knows how far the car has traveled. It doesn't know which direction it went. Imagine trying to measure a negative length with a meter stick. However, displacement can be positive or negative, since you can end up to the right or to the left of where you started. So here, we start here, and then we go to the right in the positive direction. Our displacement will be positive. However, here, If to the right is positive, but we travel to the left in the negative direction, our displacement, our delta x, will be negative. Speed has been defined as the ratio of distance and time. We've only calculated examples where the speed of the object doesn't change. It's constant. Another name for this is instantaneous speed. When an object's speed changes over time, the same formula is used to calculate its average speed. A bar is placed over the s to indicate average speed. Speed is a scalar. A scalar is a number that does not have a direction. Your car speedometer reads speed. It tells you how fast you're going, but not what direction you're traveling in. What's more interesting is when we not only consider the speed of an object, but in which direction it is moving. Velocity is a vector and gives the magnitude and direction of the object's motion. It is defined as delta x over delta t, where delta x is the displacement of the object. When delta t is very small, this velocity is known as instantaneous velocity. The velocity of a moving object can be described as 15 meters per second to the east, or 15 meters per second in the positive direction, depending on the reference frame used. Speed is the magnitude of velocity under certain conditions. A vector is represented as an arrow, where the length of the arrow represents the magnitude. Here, the vector above shows that the object's initial velocity is 10 meters per second. The vector here shows that the object's current or final velocity is 20 meters per second. You can see that the length of the arrow is twice as long to represent twice as much speed. Sometimes during an object's motion, its velocity will change. For instance, if you're driving to the grocery store, there may be a highway where the car travels quickly, and there may be stop signs where the car's velocity is 0. The average velocity for the trip can be found by dividing the total displacement by the total elapsed time. The symbol for average velocity is v with a bar over it. The average velocity can be positive, negative, or 0, depending on the motion with respect to the starting point. The average velocity can't tell us the velocity at every moment in time. It's just the average for the entire trip. Continuing with our trip to the grocery store, when the car stops at a stop sign, we say that its instantaneous velocity is 0. The instantaneous velocity is the velocity of an object at a very brief moment in time. Mathematically, it's when time is approaching 0. So the time span, the amount of elapsed time, is getting very small. That's going to give us instantaneous velocity. The instantaneous velocity can also be positive, negative, or 0, depending on the motion. A scalar is a quantity that has only a magnitude, a number, or a value. A vector is a quantity that has both a magnitude and a direction. Which of the following of these are vectors? Which are scalars? Time, distance, and speed are all scalars. They don't have direction. They're just a number or a value. Displacement and velocity, these are physics terms that are vectors that we're going to use in this class a lot. The directions of velocity and acceleration vectors are important. If an object's velocity vector and acceleration vector are pointing in the same direction, the object will speed up. So here we have an object moving to the right in the positive direction. It's also accelerating to the right in the positive direction. Therefore, it speeds up. Even if both are negative, so this object's moving to the left in the negative direction. However, it is also accelerating in the negative direction. Therefore, this object also speeds up. If an object's velocity vector and acceleration vector are pointing in opposite directions, the object will slow down. So this object's moving in the positive direction, but it has an acceleration in the negative direction. It will slow down. And vice versa. This one over here is traveling in the negative direction, but it's accelerating to the right, which means it slows down. These rules also hold true for the vertical dimension. So here, this is still one-dimensional motion, but in this case, we're using the y-axis instead of the x-axis. So here, if you have an object moving upwards, but its acceleration is down, it's going to slow down. Whereas if an object is traveling down and accelerating down, it will speed up. This particular example will be very useful to use when we study objects in free fall later in this unit. What is the average speed of the object during the time interval from 0.3 to 0.8 seconds, given the graph to the right? All right, so if we want to find average speed, we're going to take those 2 points, we're going to label them, and we're going to find the slope between those 2 points. So if you just draw a line straight from that point to that point, find the slope of that line. That will give you average speed. In this case, it is 0.996 or 1 meter per second. What is the instantaneous velocity of this object at exactly 0.4 seconds? This is different than average speed. Instantaneous velocity, we need to draw a tangent line to the graph at that point. So see how it's a curve? We need to draw a tangent line. A tangent line is a line that only touches the curve in exactly one spot. Then we need to find the slope of that line. So you can see here, we have a point over here on that same line. We calculate the slope, and it's 0.5 meters per second.